From the very beginning of human thought, reality has been questioned. When ancient thinkers first looked at the night sky filled with stars, they asked themselves whether what they saw was the true essence of existence, or just shadows of something deeper. Plato spoke of a cave where prisoners saw only flickering images on a wall, mistaking them for truth. Aristotle, though more grounded in nature, believed that everything had a fixed essence, a purpose written into the structure of the universe. Centuries later, René Descartes challenged the certainty of perception by doubting everything except the act of thinking itself. These philosophical beginnings show us that reality has never been taken for granted. It has always been something fragile, something that needed to be questioned, tested, and redefined. The rise of science shifted the way humans defined what is real. When Nicolaus Copernicus proposed that the Earth moves around the Sun rather than standing at the center of the universe, he did more than just rearrange planets. He redefined reality itself. What seemed obvious to the senses, the rising and setting of the Sun, was revealed as an illusion caused by the Earth's rotation. Centuries later, Isaac Newton brought order to this new reality by introducing universal laws of motion and gravity. Suddenly, the universe was no longer a collection of separate happenings. It was a vast clockwork in which every motion of a falling apple or a moving planet could be explained by the same rules. For a long time, Newtonian mechanics gave humans the impression that reality was firm and predictable. Every event had a cause, and with enough knowledge one could in principle calculate the future with certainty. Reality in this view was a grand machine, perfectly ordered and entirely knowable. But even within this framework, questions about the role of measurement lingered. To know reality meant to measure it, to reduce the world to numbers that described its behavior. The telescope, the microscope, the thermometer, the spectroscope, each new tool extended the reach of human senses, turning invisible features of the universe into measurable facts. Reality became identified with what could be observed and recorded. Then came Albert Einstein, who broke open the Newtonian clockwork. With special relativity, he showed that time and space themselves were not fixed backdrops, but part of the structure of reality, changing with the speed of motion. With general relativity, he revealed that gravity was not a mysterious force, but the bending of space-time itself. Suddenly, reality was not absolute, but relative to the observer. The idea that there was a single universal frame of reference dissolved. Two observers could both be correct, even while disagreeing about the order of events. This was a profound step, but even Einstein's universe still held to determinism. Events unfolded with precise mathematical necessity, as if guided by equations written in stone. The story did not end there. As scientists peered into the atom, the very building blocks of matter, they found that Newton's and Einstein's descriptions of reality failed. Electrons did not follow neat orbits around nuclei. Light behaved sometimes as a wave, sometimes as a particle, refusing to fit into a single category. In the early 20th century, experiments revealed behavior that could not be explained by classical theories. Reality at the smallest scales seemed to resist every attempt at deterministic description. The emergence of quantum mechanics transformed the meaning of reality once again. Max Planck's discovery that energy came in discrete packets called quanta was the first crack in the old picture. Einstein expanded this idea when he explained the photoelectric effect, showing that light itself arrived in quanta now called photons. Then came Niels Bohr with his Copenhagen interpretation, Werner Heisenberg with the principle of uncertainty, and Erwin Schrödinger with his wave equation. Suddenly, the notion that reality was fixed and predictable crumbled. The act of observing no longer simply revealed what was there. It seemed to participate in shaping what was real. The famous double-slit experiment confirmed this unsettling view. When particles such as electrons or photons passed through two slits, they produced interference patterns like waves. But when measured as particles, they behaved like tiny bullets, choosing one slit or the other. Even stranger, if no one looked to see which slit they went through, the interference pattern returned. The implication was clear. Reality at the quantum level was not independent of observation. The outcome seemed to depend on whether it was being watched. This was not just a philosophical puzzle. It was verified fact, supported by experiments across decades. The Stern-Gerlach experiment showed that particles like silver atoms could exist in superpositions of spin states until measured. Electron diffraction revealed that matter itself carried wave-like properties. Each result reinforced the same message. Reality at the smallest scales was not a machine, but a tapestry woven with probability, noise, and uncertainty. By the time the 20th century closed, the very concept of reality had changed multiple times. From Platonic ideals to Newtonian determinism, from Einstein's relativity to quantum mechanics, each shift showed that what humans considered reality was never final. It was always provisional, always waiting for the next revolution. Today, at the start of the 21st century, physics faces the challenge of understanding whether reality itself is fundamentally noisy, built from quantum fluctuations that cannot be eliminated. The question is not whether the universe contains noise, but whether noise is the essence of the universe itself. The transition from classical certainty to quantum unpredictability did not happen overnight. At first, many scientists resisted the idea that randomness could be woven into the fabric of reality. Einstein himself famously declared that he could not believe that God plays dice with the universe. For him, the world had to be orderly, guided by laws that left no room for chance. Yet experiment after experiment revealed that the dice were indeed part of nature's game. The more precise the measurements, the clearer the role of probability became. It was not simply a matter of hidden details waiting to be uncovered. It was something deeper, a fundamental limit on what reality could reveal. The principle of uncertainty captured this limit. According to Heisenberg, the position and momentum of a particle could not be known at the same time with absolute precision. The more one narrowed down the location, the more uncertain the velocity became. This was not because of clumsy instruments or lack of skill. It was not an error to be fixed. It was a feature of reality itself. Nature placed a boundary around knowledge. Beyond that boundary, certainty dissolved into probability. This realization forced science to accept a new kind of reality. Instead of describing particles as tiny marbles following clear trajectories, physicists spoke of wave functions, mathematical descriptions that contained probabilities rather than definite outcomes. A particle was not here or there until measured. It was described by a cloud of possibilities, a distribution of chances. When measured, the wave function appeared to collapse into one result. Before that, it was as though reality itself was undecided. For philosophers, this struck at the very foundation of what it means to say something exists. If an electron is not in one place or another until observed, in what sense is it real? For scientists, the answer was pragmatic. Reality was whatever gave measurable, repeatable results. If the equations worked, if the predictions matched the data, then the theory was accepted. Quantum mechanics passed this test again and again. Its accuracy in predicting atomic spectra, semiconductor behavior, and chemical bonds was unmatched. Even if its implications were strange, its reliability could not be denied. The role of observation became central. In the classical world, measurement simply revealed what was already true. In the quantum world, measurements seemed to select a truth from among many possibilities. This did not mean that human consciousness created reality, as some misinterpretations later claimed. Rather, it meant that the act of interaction between system and observer, whether the observer was a human eye or a particle detector, brought about definite outcomes. The quantum world resisted being described as having properties independent of such interactions. This picture was unsettling but also fertile. It spurred new interpretations and new debates. Bohr and his followers argued that reality had to be described in terms of measurements and probabilities. Others sought deeper explanations, hidden variables that might restore determinism. Yet experiment after experiment, from Bell's inequalities to modern quantum entanglement tests, consistently favored the probabilistic view. If hidden variables exist, they must operate in ways stranger than even Einstein had imagined, involving non-local connections that defy classical intuition. All of this reshaped not only physics, but the very idea of reality. In the Newtonian universe, one could imagine a vast ledger of facts, every position, every velocity, every force, written clearly. In the quantum universe, reality was no longer a ledger, but a cloud, a haze of possibilities, constantly shifting and collapsing into outcomes. It was reality in motion, reality that could not be frozen into a single definitive picture without losing its essence. Still, the picture was not one of chaos. The probabilities followed precise mathematical rules. Schrödinger's wave equation described how they evolved over time. Quantum theory had a strange dual nature, randomness at the level of individual events, yet strict order in the behavior of ensembles. A single atom might decay at an unpredictable moment, but the average half-life of many atoms could be predicted with extraordinary accuracy. It was as though reality was written in the language of chance, yet guided by laws that shaped those chances into patterns. For many, this was the most profound shift in the definition of reality since humans began to think about it. The ancients had asked whether what we perceive is illusion or truth. The Newtonians had believed in a fixed, calculable order. Einstein had shown that time and space themselves were malleable. Now quantum mechanics declared that at its core, reality was probabilistic. The fabric of existence was not woven of certainty, but of possibilities. The implications of this shift reached far beyond physics. In philosophy, it challenged notions of determinism and free will. In technology, it opened the door to inventions like semiconductors, lasers, and eventually quantum computers. In cosmology, it suggested that even the structure of the universe might have emerged from quantum fluctuations. Reality as humans experience it solid, predictable, seemingly stable, might be nothing more than the averaged outcome of countless tiny uncertainties. As the 20th century advanced, scientists began to see quantum mechanics not as a curiosity, but as the foundation of reality. Everything from the stability of atoms to the chemistry of life depended on quantum principles. Without the probabilistic behavior of electrons, there would be no stable matter, no stars shining in the sky, no molecules forming the basis of biology. What had once seemed like noise, an unwanted randomness in the equations, turned out to be essential for existence itself. And yet, the unease remained. If reality is built on noise, what does that say about truth? Is the universe ultimately knowable, or only describable in terms of probabilities? The question lingered in laboratories and lecture halls alike. Scientists pressed forward with calculations and experiments, refining their understanding. Philosophers debated the meaning of these findings. Ordinary people marveled at a universe stranger than any myth. The stage was set for the chapters that followed, where quantum noise would be examined not only as a limitation, but as a source of information, order, and even life. Reality was no longer the firm structure envisioned by Newton. It was a dance of uncertainty, a chorus of probabilities. The challenge now was to understand how this noisy foundation could give rise to the ordered world we see around us. The deeper scientists looked into the quantum world, the more reality seemed to resist ordinary intuition. It was not only about particles behaving like waves, or probabilities replacing certainties. It was about the realization that human categories of thought were not enough to capture what truly happens at the smallest scales. The very language of reality needed to be rewritten. Classical words such as position, trajectory, or even particle and wave were no longer sufficient. Instead, physicists used wave functions, probability amplitudes, and operators, abstract tools that pointed to a reality beyond direct visualization. The strangeness of this reality was vividly revealed through the phenomenon of entanglement. When two particles interact in certain ways, they can become linked, so that measuring one immediately tells you something about the other, even if they are separated by vast distances. This correlation defies any simple picture of independent objects. To Einstein, it seemed like a spooky action at a distance, something unacceptable. Yet careful experiments in the late 20th century, especially those inspired by John Bell's work, confirmed that entanglement is real. Reality at the quantum level is not built from isolated parts, but from interconnected wholes. The universe, at its foundation, behaves like a web of relationships, not like a set of self-contained pieces. What does this mean for the concept of reality itself? For one thing, It shows that the assumption of separability, so natural in classical thought, does not apply universally. In the classical world, one can describe an apple without mentioning the table it sits on. In the quantum world, a particle cannot always be described without reference to the system it is entangled with. This forces a shift in the definition of what is real. Reality is not simply the collection of properties possessed by things. It is the structure of correlations, the patterns of information that exist between them. This perspective may feel abstract, but it has very concrete consequences. Without entanglement, quantum computers could not exist. Without quantum fluctuations, stars could not fuse hydrogen into helium. The very stability of matter depends on the strange rules of quantum mechanics. What once seemed like noise turns out to be the key ingredient of order. The old dream of certainty, of predicting every detail of reality, gives way to a subtler vision in which probability and uncertainty are not enemies of knowledge, but the terms on which knowledge is possible. The act of measurement illustrates this paradox. Every time a detector clicks, every time a scientist records an outcome, an unpredictable event has become a fact. Out of the haze of possibilities, one result emerges, irreversible and real. The rules of probability dictate the chances, but the specific outcome is unknowable until it happens. In this way, reality is constantly crystallizing out of uncertainty, moment by moment. What appears to human senses as a continuous, stable world is the ongoing product of countless quantum events solidifying into facts. To appreciate how radical this view is, imagine rewinding the history of science. Ancient philosophers sought permanent truths behind appearances. Newton imagined laws that would hold forever, applicable to all motions. Einstein reshaped space and time, but still believed in an underlying order. Quantum mechanics, however, teaches that at the foundation of existence, there is not permanence, but fluctuation, not certainty, but probability. This does not make reality unreal. It makes it more dynamic, more subtle, and more astonishing than any previous picture. The challenge for humans is to live with this understanding. On one hand, quantum mechanics gives unparalleled predictive power. It explains the behavior of atoms, enables modern electronics, and underlies technologies that shape daily life. On the other hand, it denies the comfort of absolute certainty. It tells us that the universe is not a machine rolling forward in complete predictability. Instead, it is a process in which randomness and law are intertwined. In this sense, the illusion of emptiness is shattered. What once seemed like empty space is in fact alive with fluctuations. What once seemed like solid certainty is revealed as a play of probabilities. The ground beneath human feet is not absolute, but it is real enough to support life, thought, and discovery. Reality is not less because it is noisy. It is more. Its richness comes precisely from the interplay between order and uncertainty. As the 20th century turned into the 21st, this view of reality became the foundation for new frontiers of science. Researchers began to ask whether noise itself could be harnessed as a resource. They explored how randomness gives rise to order, how fluctuations shape the cosmos, how the brain may even use uncertainty to function. The story of reality had shifted once again. It was no longer about eliminating noise, but about understanding it, living with it, and even thriving because of it. Thus ends the opening chapter of this exploration. From ancient philosophy to modern physics, from Plato's cave to the double-slit experiment, the question of what is real has led to one revolution after another. Each revolution has brought humans closer to a deeper truth, even as it unsettles their assumptions. The next step is to look more closely at the birth of quantum mechanics itself, to see how a handful of puzzling experiments forced the most profound transformation in the history of science. The journey continues into the very heart of quantum noise. At the dawn of the 20th century, physics stood at what many thought was its triumphant peak. Newton's mechanics seemed to describe motion with perfect clarity. Maxwell's equations unified electricity, magnetism, and light into a single framework. Thermodynamics explained heat and energy with increasing precision. To many physicists, it appeared that science was approaching closure, that the great mysteries of nature had been solved, and only minor details remained to be filled in. Yet hidden beneath this confidence were cracks that would soon widen into a revolution. One of the first cracks appeared in the study of blackbody radiation, the spectrum of light emitted by a hot object. Classical physics predicted that as frequency increased, the emitted energy should grow without bound, leading to what was called the ultraviolet catastrophe. Experiments showed no such thing. Instead, the intensity rose to a peak and then declined. In 1900, Max Planck proposed a bold solution. He suggested that energy was not continuous but came in discrete packets, quanta, proportional to frequency. This idea was at first a mathematical trick to fit the data, but it contained the seed of a new physics. Reality, it seemed, was granular at its foundations. Albert Einstein carried Planck's insight further in 1905 when he explained the photoelectric effect. Light, shining on a metal surface, could eject electrons, but only if the light frequency exceeded a certain threshold. Classical wave theory could not explain this abrupt cutoff. Einstein proposed that light itself was made of quanta, later called photons. The energy of each photon was proportional to its frequency. This radical idea earned him the Nobel Prize and opened the door to a new understanding of light and matter. The breakthroughs did not stop there. In the following decades, the strange behavior of electrons, atoms, and radiation demanded new theories. Niels Bohr proposed his model of the atom in 1913, with electrons in quantized orbits around the nucleus. Though primitive by later standards, it explained the discrete spectral lines of hydrogen, which classical physics could not. The atom, once thought of as a miniature solar system, revealed itself to be governed by rules far removed from ordinary mechanics. By the 1920s, two distinct but complementary formulations of quantum theory emerged. Erwin Schrödinger introduced wave mechanics, describing particles as wave functions that evolve smoothly according to a differential equation. Werner Heisenberg, working independently, developed matrix mechanics, a more abstract but equally powerful approach. Both were shown to be mathematically equivalent. At their heart was the same message: particles do not have definite positions and velocities until measured, but exist in states described by probabilities. Heisenberg crystallized this view with his principle of uncertainty. The more precisely one measures a particle's position, the less precisely one can know its momentum, and vice versa. This was not due to experimental error, but an inherent property of nature. Reality imposed limits on what could be known simultaneously. Bohr offered a philosophical interpretation, later called the Copenhagen interpretation, which emphasized that quantum mechanics does not describe an objective reality independent of observation. Instead, it provides probabilities for outcomes of measurements. The act of measurement, in this view, is fundamental. Reality is not fully determined until interaction brings about a result. These ideas, strange as they seemed, were quickly tested in laboratories. The double-slit experiment demonstrated the dual nature of particles, acting like waves when unobserved and like localized impacts when measured. The Stern-Gerlach experiment in 1922 showed that atomic particles have quantized spin values, not continuous orientations. In 1927, Davison and Germer confirmed that electrons could diffract like waves, proving that matter itself exhibits wave-particle duality. Each experiment deepened the mystery, yet also solidified the theory. Quantum mechanics, despite its strangeness, explained data that classical physics could not touch. It became the essential framework for atomic and subatomic science. By the late 1920s, the birth of quantum mechanics was complete. It was a new way of thinking about reality, where probabilities replaced certainties, and noise was not a flaw, but a foundation. The new quantum theory spread rapidly, carried by its ability to explain puzzles that had defeated classical science for decades. One striking example was the stability of atoms. According to Newtonian mechanics and Maxwell's electrodynamics, electrons orbiting a nucleus, should radiate energy and spiral inward, collapsing the atom within a fraction of a second. Yet matter clearly persisted. Quantum mechanics solved this by showing that electrons occupy discrete energy levels. They cannot exist in between, and they do not lose energy while remaining in a stable state. The very existence of solid matter, of chemistry, and of life itself depended on these rules. What had seemed an impossible paradox under classical laws became natural within the quantum framework. The double-slit experiment offered perhaps the most dramatic window into this new world. When a beam of light passed through two slits and struck a screen, it produced an interference pattern typical of waves. That was already known, but when individual photons were sent through one at a time, they still built up the same interference pattern, as if each photon had traveled through both slits at once. The same behavior was observed with electrons, atoms, even molecules. It was as though every particle carried with it a cloud of possibilities until observed, when it resolved into a definite outcome. The image of reality as a solid chain of causes and effects gave way to a subtler vision of overlapping probabilities and wave-like behavior. By the late 1920s, physicists recognized that quantum mechanics was not a passing oddity, but a fundamental theory. Schrödinger's wave mechanics provided precise tools for calculating atomic spectra and chemical bonds. Heisenberg's uncertainty principle established the boundaries of what knowledge was possible. Bohr's Copenhagen interpretation guided many in making sense of the strange results. Yet not all were convinced. Einstein remained skeptical, insisting that quantum mechanics must be incomplete. He hoped that hidden variables, still undiscovered, could restore determinism. Alongside colleagues like Boris Podolsky and Nathan Rosen, he proposed thought experiments to challenge the probabilistic view. But later experiments, especially those testing Bell's inequalities in the mid-20th century, consistently favored the quantum picture. Despite philosophical debates, the practical power of quantum mechanics was undeniable. It explained the periodic table, predicted the properties of semiconductors, and laid the foundation for modern electronics. The invention of the transistor in 1947, which depended on quantum understanding of materials, launched the digital age. Lasers, magnetic resonance imaging, and countless other technologies emerged directly from the strange rules of the quantum world. In every case, predictions matched reality, with precision far exceeding classical physics. The rapid development of the theory also produced new concepts that challenged common sense. The notion of superposition, where a system exists in multiple possible states, at once until measured, defied ordinary logic. Schrödinger dramatized this with his famous thought experiment of a cat that could be both alive and dead until observed. Though the scenario was exaggerated, it highlighted the unsettling gap between microscopic rules and macroscopic experience. Somehow, the fuzziness of the quantum world gave way to the solidity of everyday life. How this transition occurred became a central question for decades to come. Meanwhile, quantum mechanics reshaped the relationship between observation and reality. In classical science, measurement was passive. One simply recorded what was there. In quantum mechanics, measurement was active, bringing about outcomes that were not definite beforehand. The universe was no longer imagined as a book written in advance, waiting to be read. It was more like a story unfolding as interactions occurred. For many, this was the most radical departure from past thinking. It suggested that uncertainty was not an imperfection of human knowledge, but a property of existence itself. As the community of physicists wrestled with these ideas, a generation of brilliant minds carried the theory forward. Paul Dirac developed an equation that united quantum mechanics with special relativity, predicting the existence of antimatter. Wolfgang Pauli introduced the exclusion principle, explaining why electrons arrange themselves in shells and giving rise to the structure of the periodic table. Louis de Broglie proposed that matter has wave properties, a hypothesis soon confirmed by experiment. Each step reinforced the sense that reality was stranger and richer than previously imagined. By the end of the 1920s, the foundation of quantum mechanics was firmly in place. Though questions remained about interpretation, the formalism worked with unmatched accuracy. It had passed every experimental test, explained phenomena across physics and chemistry, and opened doors to technological revolutions. The old dream of a perfectly deterministic universe had been replaced by a new reality, one where probability and uncertainty were woven into the very fabric of existence. The birth of quantum mechanics was complete, but its implications were only beginning to unfold. The transition from the classical to the quantum world did more than solve specific puzzles of physics. It redefined what it meant to understand nature. Before the 20th century, to understand something was to reduce it to precise mechanisms, to write down its causes in terms of forces and motions. After the arrival of quantum mechanics, understanding shifted to accepting probabilities, symmetries, and abstract mathematical rules as the foundation of knowledge. This was not an abandonment of rigor, but an expansion of it, a recognition that the laws of nature were written in a language that did not conform to everyday expectations. One of the most striking lessons of this period was that randomness and certainty were not opposites but partners. The decay of a single radioactive atom could not be predicted in detail. Yet the collective behavior of many atoms was so reliable that it became the basis for nuclear clocks. Quantum uncertainty, far from being a flaw, was the reason certain systems behaved with such regularity at larger scales. The discovery that randomness could yield stability was shocking, but it became a cornerstone of modern science. This new vision of reality also forced scientists to grapple with philosophical questions. If measurement brought about outcomes, what counted as a measurement? Was the presence of a conscious observer required, or could any interaction with the environment serve? The debates between Einstein, Bohr, Schrödinger, and others echoed through conferences and letters, shaping the intellectual climate of the age. Bohr insisted that physics was not about uncovering an independent reality, but about describing observations in consistent language. Einstein refused to let go of the idea that something deeper must exist behind the probabilities. Schrödinger, both a founder and a critic, revealed the paradoxes with thought experiments that remain famous today. These discussions showed that quantum mechanics was not only a scientific revolution, but also a philosophical one. Despite the debates, the experimental evidence always returned to the same conclusion: quantum theory worked. The more carefully it was tested, the more accurate it proved to be. Spectroscopic lines matched predictions to many decimal places. The magnetic properties of atoms, measured with precision, agreed with theoretical calculations. Even phenomena unimaginable before, like superconductivity, where resistance vanished in certain materials, could be explained only with quantum ideas. Each success reinforced the legitimacy of the theory, making it not just a temporary patch but the foundation of physics. The story of the birth of quantum mechanics is therefore the story of a profound shift in human thought. From Planck's discovery of quantization to Einstein's photons, from Bohr's atomic model to Schrödinger's wave equation and Heisenberg's uncertainty principle, the picture of reality was rewritten in less than 3 decades. What began as desperate attempts to explain anomalies became a coherent framework that overturned centuries of assumptions. The world was no longer governed by certainty at its smallest scales. Instead, it was a place where possibility and actuality intertwined, where noise was not an intruder, but a fundamental feature of existence. This transformation prepared the ground for everything that followed. Later generations would explore how this intrinsic randomness shapes information, how noise at the smallest scales can generate order at larger ones, how the universe itself may have emerged from fluctuations during its earliest moments. But to understand any of that, it was necessary first to grasp that quantum mechanics was not just a new theory. It was a new reality, one in which probability and uncertainty were as real as mass and energy. Thus, the birth of quantum mechanics was not a mere scientific event, but a turning point in human history. It was the moment when reality itself was revealed to be different from what centuries of philosophy and science had assumed. From that point on, no description of the universe could ignore the strange and beautiful fact that chance was built into the core of existence. And it is from this realization that the idea of quantum noise, the ever-present fluctuations of reality, would grow, shaping the path of physics, technology, and human thought in the decades to come. At the heart of quantum mechanics lies a concept that is both unsettling and illuminating: quantum noise. Unlike the noise we encounter in everyday life, the hiss of static on a radio, or the grainy flicker of an old television screen, quantum noise is not the result of human imperfection or faulty equipment. It is not something that can be removed by building better instruments or refining our techniques. It is a fundamental property of reality, a consequence of the laws that govern the smallest scales of nature. Physicists often describe this noise as the unavoidable fluctuations of fields and particles that persist even in the absence of matter or energy. Imagine a perfect vacuum stripped of every atom, colder than the darkest interstellar void. Even there, when all else is removed, tiny fluctuations continue. The vacuum is not truly empty, but filled with restless activity, pairs of particles appearing and vanishing, fields vibrating with zero-point energy. This background hum of existence cannot be switched off. It is part of what it means for reality to exist at all. The seeds of this understanding lie in Heisenberg's principle of uncertainty. The principle tells us that no particle can have both its position and momentum defined with absolute precision. The more one narrows down its location, the more uncertain its velocity becomes, and vice versa. This uncertainty is not a reflection of ignorance. It is not that hidden details are waiting to be discovered. Rather, it is that the world itself does not allow such sharpness. In the quantum world, fuzziness is built in. When one calculates the energy of a field, this uncertainty prevents it from ever being exactly zero. The result is the presence of irreducible fluctuations, what physicists call zero-point motion. Evidence of this subtle noise has appeared again and again in experiment. One of the most famous demonstrations is the Casimir effect, predicted in 1948 and later confirmed. Two uncharged metal plates placed very close together in a vacuum experience an attractive force, as if pulled by invisible hands. This force arises from the suppression of vacuum fluctuations between the plates, compared with those outside. The plates feel the difference in quantum noise pressing upon them. Another piece of evidence comes from the Lamb shift observed in hydrogen atom. Tiny differences in energy levels, inexplicable by classical theory, arise from the interaction of electrons with vacuum fluctuations. These effects reveal that noise is not an artifact of measurement, but a measurable feature of nature itself. For everyday experience, quantum noise is invisible, hidden beneath the scale of atoms and fields. But at the fundamental level, it shapes everything. Without zero-point energy, atoms could not exist in stable configurations. Without fluctuations, transitions in matter and radiation would not occur in the same way. What seems random and meaningless at first glance is in fact the foundation of order. Still, the strangeness of this noise unsettled even the pioneers of physics. For centuries, science had advanced by reducing uncertainty, by sharpening measurements and refining equations. Now, physicists faced the possibility that uncertainty was not a temporary obstacle but an eternal feature. The question was no longer how to eliminate noise but how to understand it, to see it as a building block rather than a flaw. The quantum world tells us that reality is never perfectly quiet. Beneath the calm of classical order, there is always motion, always fluctuation, always a murmur of chance. The challenge is to comprehend how such randomness can give rise to the stability and complexity we observe at larger scales. That journey begins with the recognition that noise is not the opposite of knowledge, but the canvas upon which knowledge is painted. The principle of uncertainty is often described in terms of measurement, but its meaning goes far beyond the limits of instruments. It represents a truth about the structure of nature itself. When Werner Heisenberg first formulated it in 1927, he framed it as a relation between position and momentum, quantities that could not be known simultaneously with arbitrary precision. Later developments extended the principle to many other pairs of properties, such as energy and time. The message was universal. At the quantum scale, certainty dissolves into a spread of possibilities, a distribution governed by probability. This is the root of what we call quantum noise. To understand why this matters, Imagine an electron bound inside an atom. According to classical reasoning, if the electron were perfectly still, it could sit exactly at the nucleus. But the uncertainty principle forbids this. To localize the electron completely would require infinite uncertainty in its momentum, which is impossible. Instead, the electron occupies a fuzzy region of space, described by a wave function. The atom is stable not in spite of uncertainty, but because of it. The restless motion imposed by quantum noise prevents collapse, allowing matter to persist. In this sense, uncertainty is not a defect, but a safeguard of existence. This constant hum of fluctuations does not stay confined to atomic systems. It manifests in subtle but profound ways across the universe. The Lamb shift in hydrogen, detected in 1947 by Willis Lamb and Robert Rutherford, revealed that the energy levels of electrons were shifted slightly by their interactions with the quantum vacuum. Such a small effect would have been invisible to classical theories, yet it was measured with precision and matched the predictions of quantum electrodynamics. The vacuum, once imagined as a silent void, proved to be an active participant in shaping the behavior of matter. The Casimir effect, first predicted by Hendrik Casimir in the same year, made the presence of quantum fluctuations even more tangible. When two plates are placed extremely close together in a vacuum, the range of wavelengths that can exist between them is restricted, while outside the plates, fluctuations of all wavelengths persist. This imbalance generates a measurable force, drawing the plates together. Though tiny, this effect has been verified in laboratory experiments and is now part of the practical challenges in designing micro and nanoscale devices. The very fabric of emptiness, far from being still, exerts pressure on the material world. Yet quantum noise is not confined only to these exotic experiments. It is present in every act of measurement, every attempt to probe the microcosm. No detector, no matter how refined, can escape it. Photons arrive at random intervals. Electrons scatter unpredictably. Atoms decay at uncertain times. When one zooms into the foundations of reality, certainty slips away and probabilities take its place. The universe is not a static book of facts, but a continuous unfolding of possibilities into outcomes. This leads naturally to the idea of decoherence, the process by which quantum systems lose their fragile superpositions and appear classical. When a particle exists in a superposition of states, its wave function includes multiple possibilities at once. But in contact with its environment, it interacts with countless other particles, and those interactions effectively entangle it with the world. The coherent quantum state spreads out into the environment, and the neat interference patterns vanish. The result is that the system appears to have taken on a definite state, even though at the deepest level, it remains governed by quantum rules. Decoherence explains why humans do not see macroscopic objects like cats or chairs in superpositions. It shows how the noisy environment of the real world transforms quantum possibilities into classical facts. Laboratory evidence for decoherence has grown over the past decades. Experiments with trapped ions, superconducting qubits, and photons in optical cavities have revealed how fragile superpositions collapse when exposed to noise. Quantum computers, which rely on maintaining coherence, must battle against this constant tendency of reality to entangle systems with their surroundings. The fight to control decoherence is one of the defining challenges of modern physics and technology, underscoring the ever-present role of quantum noise. Seen in this light, uncertainty is not only a constraint but also a bridge. It connects the microscopic world of superpositions and fluctuations with the macroscopic world of stable outcomes. It explains how atoms remain intact, how energy levels shift, how empty space exerts forces, and how quantum possibilities solidify into the definite experiences of daily life. The noise is not random chaos but structured unpredictability, guided by precise mathematical rules. It is the pulse of the universe at its most fundamental level. The presence of quantum noise forces us to rethink what it means to know something with certainty. For centuries, the goal of science was to strip away randomness, to reach a pure and deterministic description of nature. Newton's laws gave the impression that with enough knowledge of initial conditions, the entire future could be predicted. The discovery of quantum mechanics overturned this vision. Instead of determinism, we encounter probabilities. Instead of certainties, we deal with distributions. The universe is not a mechanism grinding forward with absolute inevitability, but a process shaped by noise at every level. And yet, this noise is not without order. It follows strict statistical rules, as if the dice of the universe were weighted in precise ways. Radioactive decay offers a perfect example. No one can say when a single atom of uranium will release an alpha particle. It might happen within a second, or not for millions of years. But gather enough atoms, and their average half-life becomes an unshakable constant. Entire industries, from medicine to geology, depend on the reliability of this probabilistic law. The apparent randomness at the level of the individual atom generates predictability at the level of large numbers. This duality between chaos and order is one of the defining features of quantum noise. Experiments continue to reveal the subtle ways in which vacuum fluctuations influence reality. In modern particle accelerators, collisions between high-energy particles produce results shaped not only by the colliding beams, but also by the sea of virtual particles flickering in and out of existence. These virtual processes leave measurable imprints, corrections to scattering rates and masses that must be included to match experimental data. In cosmology, theories of the early universe rely on the idea that quantum fluctuations, magnified during cosmic inflation, seeded the distribution of galaxies across the sky. The faint ripples measured in the cosmic microwave background are often described as fossilized quantum noise, preserved for billions of years. What begins as uncertainty at the smallest scales can grow to shape the largest structures in the cosmos. Even at the frontier of precision measurement, quantum noise sets ultimate boundaries. Gravitational wave detectors like LIGO are so sensitive that they measure changes in length smaller than a proton's width, yet their performance is limited by quantum fluctuations in the laser light itself. Scientists have developed clever techniques, such as squeezed light, to reduce the impact of this noise, but it can never be eliminated entirely. The lesson is humbling. No matter how advanced technology becomes, the universe always preserves a core of unpredictability. For some, this constant presence of noise suggests that reality is not something solid and absolute, but something emergent, something that crystallizes out of fluctuations. The quantum world is restless, a field of possibilities in motion. Out of this restlessness comes stability, complexity, and ultimately, life. Noise, in this sense, is not the opposite of meaning but the condition for it. Without uncertainty, there would be no variation, no creativity, no chance for order to arise. The challenge for human thought is to embrace this paradox. Noise undermines certainty, but it also provides the foundation upon which certainty can be built. It erodes the dream of absolute knowledge, but it opens the door to understanding the universe in richer ways. In science, acknowledging quantum noise has led to deeper insights and groundbreaking technologies. In philosophy, it has forced a re-examination of the very nature of reality and knowledge. Thus, the chapter on quantum noise and uncertainty closes with a recognition that randomness is not an intruder in the cosmos, but a resident. It cannot be wished away or bypassed. It is woven into the very fabric of existence. The question that remains is how to distinguish between signal and noise, how to find meaning within the uncertainty. This is the task that information, theory, thermodynamics, and modern science have taken up, and it is where the story now turns. When physicists speak of quantum noise, they often emphasize its role as a fundamental limit, a boundary on what can be known. But to understand noise fully, one must consider its relationship to signal. Noise is not merely randomness, it is randomness measured against meaning. The crackle of static on a radio is noise only because we expect to hear music or speech. Without the expectation of signal, the static would be nothing at all, only the sound of existence itself. The modern understanding of signal and noise began not in physics but in communication theory. In the mid-20th century, Claude Shannon, working at Bell Labs, developed the mathematical foundation of information theory. He asked how messages could be sent efficiently and accurately over noisy channels, whether those channels were wires, radio waves, or even printed text. Shannon introduced a precise definition of information, measured in bits, and distinguished between signal, the meaningful content of a message, and noise, the random disturbances that obscure it. His work revealed that noise does not merely interfere with communication, but defines the limits of how much information can be transmitted. Shannon's ideas transformed not only engineering, but also the way scientists thought about randomness. He showed that uncertainty can be quantified, that entropy, a measure of unpredictability, is central to understanding information. A perfectly predictable message carries no information, while a completely random one carries no usable meaning. Information lies in the balance between order and randomness, between signal and noise. This insight resonated far beyond telephones and telegraphs. It connected to the older concept of entropy in thermodynamics, where disorder measures the number of possible arrangements of a system. In physics, entropy had long been associated with the second law of thermodynamics, which states that in any closed system, entropy tends to increase. This was seen as a measure of disorder, the spreading out of energy into less useful forms. Shannon gave this concept a new life, showing that entropy is also a measure of uncertainty, the missing information needed to fully specify a system. Suddenly, the language of physics and the language of communication were linked. Noise was not just a nuisance, but a measurable quantity, a key to understanding both machines and nature. Quantum mechanics added a deeper layer to this picture. In the classical world, noise can often be reduced by better engineering, by shielding wires, refining signals, or filtering interference. But in the quantum world, noise cannot be eliminated. Vacuum fluctuations, uncertainty relations, and irreducible randomness set hard limits on measurement and transmission. Quantum noise defines the ultimate capacity of communication channels. It tells us how much information can be extracted from light, from particles, from any physical system. The laws of quantum physics are also laws of information. This connection has practical consequences. Quantum random number generators, for example, exploit the inherent unpredictability of photon arrivals or electron tunneling to produce sequences that no algorithm could reproduce. Unlike pseudo-random numbers generated by computers, these sequences are guaranteed by physics to be unpredictable. They have become vital in encryption, ensuring secure communication in a digital age. What once seemed like useless noise is now harnessed as a resource. The boundary between signal and noise also plays out in biology. The brain processes signals from the senses in a world filled with uncertainty. The nervous system must separate meaningful patterns from random fluctuations, much as an engineer designs a receiver to decode a faint message in static. Sometimes noise itself improves perception, a phenomenon known as stochastic resonance. In such cases, the presence of a certain level of noise actually enhances the ability to detect weak signals. Here again, randomness does not only obscure meaning, it can create the conditions for meaning to emerge. As the 20th century closed, scientists began to see noise not as a defect, but as a fundamental partner of order. Information, entropy, and randomness became intertwined concepts, each helping to illuminate the others. From the equations of Shannon to the uncertainty of Heisenberg, the message was the same. The universe is not a place of pure signal or pure noise, but of interplay between the two. Meaning emerges from randomness, and randomness shapes meaning. The next step in this journey is to explore how order itself can arise from random processes, how noise at one level can produce structure at another. This is not only a question of physics, but of chemistry, biology, and even the cosmos. It asks us to see noise not as the enemy of order, but as its secret architect. The idea that noise and entropy are central to both communication and physics reshaped the scientific imagination in the 20th century. In thermodynamics, entropy had long been associated with heat dispersing, with energy spreading out until no more useful work could be done. A hot cup of coffee cools as its heat dissipates into the room. A flame burns brightly, then fades to ash and smoke. The second law insists that in any closed system, entropy must increase, a truth confirmed in every laboratory and every observation of nature. Yet what Shannon revealed was that entropy could also be seen as uncertainty, a measure of missing information. Suddenly, the spreading of heat and the uncertainty of a message were revealed as different faces of the same idea. To see why this matters, imagine a deck of cards. When ordered from ace to king, it carries little entropy because its state is predictable. Shuffle it thoroughly, and the entropy increases because the number of possible arrangements skyrockets. The analogy applies equally to molecules in a gas or bits in a message. Entropy is not simply disorder, but the number of ways something could be arranged while still appearing the same at a larger scale. In physics, this insight allows us to link the microscopic world of atoms with the macroscopic laws of thermodynamics. The noise at the smallest scales gives rise to the arrow of time we experience in daily life. This connection between entropy and time was one of the great revelations of modern science. Newton's equations were reversible. In principle, they allowed the film of the universe to run backward as easily as forward. But the second law introduced irreversibility. Heat does not flow spontaneously from cold objects to hot ones. Entropy increases, and with it comes the sense of time's arrow. From this perspective, noise and randomness are not merely background features. They are the very reason time feels like it moves forward. Quantum mechanics deepened this view by showing that even at absolute zero, when all thermal motion should vanish, fluctuations persist. 0-point energy means that no system can ever be completely still. These fluctuations, though subtle, influence everything from the stability of matter to the cosmology of the early universe. The link between entropy, noise, and the structure of the cosmos becomes clear. The universe itself may be thought of as a grand system, where randomness and order are locked in a delicate dance. In communication systems, engineers have learned to turn these truths into tools. Error-correcting codes, for example, allow reliable messages to be transmitted, even when noise corrupts parts of the signal. By adding redundancy, they use the mathematics of entropy to fight against uncertainty. Similarly, in thermodynamics, living organisms appear to defy the second law by creating order out of chaos. But this is only possible because they are open systems, constantly exchanging energy with their environment. The entropy of the universe still rises, even as life builds local pockets of complexity. From molecules to messages, from the cooling of stars to the storage of data, entropy defines the limits of possibility. Noise, rather than being eliminated, must be managed, harnessed, and sometimes even welcomed. When scientists speak of entropy in physics or Shannon entropy in information theory, they are referring to the same underlying principle. The more uncertainty, the higher the entropy. The more order, the lower it. Both perspectives reveal that noise is not peripheral, but central to understanding how systems evolve, communicate, and endure. This recognition prepared the way for new ideas about how randomness can produce order. Brownian motion, the ceaseless jittering of particles suspended in liquid, once puzzled observers until it was recognized as evidence of molecular motion. The discovery that apparent chaos at small scales can lead to predictable patterns at larger ones opened a path to statistical mechanics, the bridge between the microscopic and macroscopic. What once seemed like meaningless noise turned out to be the signature of hidden order. As physics advanced, the same lesson repeated itself. Noise could be destructive, but it could also be generative. The line between the two depended not on the existence of noise, but on how it interacted with structure. The universe was not a contest between silence and signal, but a composition in which noise supplied the rhythm, the raw material, out of which order emerged. When Shannon introduced his measure of information, he revealed that noise could never be entirely removed, but only balanced. A channel free of noise would carry no new information because every signal would be perfectly predictable. A channel swamped by noise would also fail because no pattern could be extracted. The usefulness of communication lies between these extremes, where uncertainty is present but bounded, where signal stands out against the background. This insight applies not only to telephones and computers, but to the entire fabric of nature. Information is defined against noise, and noise in turn gives context to information. In quantum physics, this relationship becomes even sharper. Every attempt to extract information from a quantum system disturbs it, a consequence of the uncertainty principle. The more precisely one measures, the more uncertainty is introduced elsewhere. The act of measurement is not passive, but participatory. Quantum information theory, a field that emerged in the late 20th century, formalized these truths, showing how entanglement, superposition, and decoherence all obey limits defined by noise. The bits of classical computing became qubits, units that embody uncertainty as a resource rather than a problem. The concept of entropy in this framework becomes not only a measure of disorder, but a measure of possibility. A system with high entropy is one with many potential microstates, many possible arrangements hidden beneath its surface. This richness of possibility is the soil out of which order can arise. In this sense, noise is not simply the enemy of pattern, it is the source from which patterns emerge. The static in a radio may seem meaningless, but within it, messages can be carved. The fluctuations of the quantum vacuum may seem chaotic, but out of them, the cosmos itself may have been born. The recognition of this duality transformed not only science but also philosophy. For centuries, randomness was seen as ignorance, a mark of human limitation. But modern physics showed that randomness is real, intrinsic, irreducible. At the same time, it showed that randomness does not erase meaning but helps create it. Probability distributions, entropy measures, and quantum fluctuations all reveal a universe that is not silent, but alive with uncertainty. And it is precisely in the balance between uncertainty and regularity that life, communication, and knowledge become possible. By the end of the 20th century, scientists could no longer speak of noise as something to be eliminated. They spoke, instead of managing noise, channeling it, even using it as a tool. Random number generators powered by quantum processes created security protocols beyond the reach of classical hacking. Error-correcting codes transformed noisy signals into reliable transmissions. Even in neuroscience, researchers discovered that a certain level of randomness can sharpen perception, helping organisms detect faint signals in a noisy world. Everywhere, noise was revealed not as a flaw but as a feature, a partner in the construction of order. And so the journey moves forward. Having seen how signal and noise intertwine, the next step is to examine how large-scale structures, from crystals to galaxies, emerge from the restless fluctuations of the microscopic world. This is the paradox at the heart of reality, that from randomness comes order, from uncertainty comes stability, from noise comes meaning. At first glance, randomness appears to be the enemy of order. When dice are thrown, their outcomes seem meaningless. When molecules jostle in a gas, their collisions appear chaotic. When genetic mutations occur, they arise without design. Yet again and again, science has shown that order does not exist in spite of randomness, but often because of it. The world we inhabit, from the stability of matter to the complexity of life, emerges from processes that are noisy at their foundation. The question is not whether randomness leads to order, but how. One of the earliest windows into this paradox came with the study of Brownian motion. In 1827, the botanist Robert Brown observed tiny pollen grains suspended in water, jittering ceaselessly under his microscope. At first, it was unclear whether the movement was caused by life within the grains or some hidden current in the water. Decades later, Albert Einstein provided the explanation. In 1905, he published a paper showing that the erratic paths of the pollen grains were the result of countless collisions with water molecules, themselves moving randomly due to thermal energy. The phenomenon was not a sign of disorder, but evidence for the reality of atoms, which until then remained unproven. In a profound twist, the apparent chaos of Brownian motion became one of the strongest confirmations of the atomic theory of matter. Statistical mechanics, pioneered by figures like James Clerk Maxwell and Ludwig Boltzmann, built upon this insight. Instead of describing every particle individually, it described the collective behavior of vast numbers of particles in terms of averages and probabilities. Out of randomness came predictability. The pressure of a gas, the temperature of a liquid, the diffusion of heat, all could be explained as emergent properties of countless random motions. While any one particle moved unpredictably, the ensemble followed laws as strict as those of classical mechanics. This was a turning point in science, showing that randomness could generate order at scale. The same principle reveals itself in phase transitions, where systems move from disorder to order through collective behavior. Consider water cooling into ice. At the molecular level, liquid water is a restless dance of molecules, each moving freely. As temperature drops, random fluctuations begin to favor alignment. Eventually, the molecules lock into a crystalline lattice, forming a repeating pattern that extends outward. Order emerges spontaneously from the collective play of randomness. In magnets, the random spins of electrons at high temperature gradually align as the system cools, producing a macroscopic field. In superconductors, electrons form pairs and move in perfect harmony, erasing resistance. These transitions show how structured patterns can grow out of stochastic activity, revealing a deep link between noise and order. The emergence of order from randomness is not confined to physics. In chemistry, reactions often depend on fluctuations that allow molecules to cross energy barriers and form new compounds. In biology, the role of randomness becomes even clearer. Genetic mutations, occurring by chance, provide the raw material for evolution. Natural selection does not create mutations but acts upon them, amplifying the ones that confer survival advantages. The diversity of life on Earth, from bacteria to humans, is the product of random changes filtered by natural laws. Without noise at the level of genes, there would be no adaptation, no complexity, no life. Neural dynamics provide another striking case. The brain is not a deterministic machine in which every thought follows directly from the one before. Instead, it operates in a noisy environment, where neurons fire with variability and uncertainty. This noise is not merely tolerated, but used. Research suggests that neural systems can exploit randomness to explore new patterns, to avoid becoming stuck in rigid loops, to enhance sensitivity to faint signals. Just as stochastic resonance can improve the detection of weak inputs, randomness in the brain may enhance perception and creativity. Once again, noise is not the enemy of order, but a partner in its creation. The lessons of physics, chemistry, and biology converge on a single point. Random processes, far from destroying structure, can generate it. The key lies in scale. At the level of individual events, outcomes are unpredictable. But when billions of events interact, patterns emerge. It is in this interplay that the universe finds its balance, weaving order from chance, structure from noise. The transformation of randomness into order is perhaps most vividly displayed in the collective behavior of matter as it undergoes phase transitions. When water cools and freezes into ice, each molecule begins in a state of ceaseless motion, jostling unpredictably against its neighbors. Nothing about the path of one molecule foretells the path of another. Yet as temperature falls, fluctuations begin to align. A symmetry is broken, and suddenly trillions of molecules arrange themselves into a crystalline lattice. The order stretches outward across macroscopic scales, producing ice that can be held in the hand. Out of chaotic motion emerges a pattern so stable that it can last for millennia in the heart of glaciers. The same principle governs magnetism. At high temperatures, the magnetic moments of electrons, tiny compass needles pointing in random directions, cancel one another. There is no overall magnetic field, but as the material cools, fluctuations encourage alignment. At a critical threshold, the random spins tip collectively toward order, producing a unified field. A magnet, which appears to embody coherence and stability, is in fact born from countless random motions that self-organize under the right conditions. Superconductivity offers an even more striking case. In ordinary metals, electrons scatter unpredictably, producing resistance and heating wires when current flows. But under certain conditions, these very electrons, buffeted by fluctuations in the lattice of atoms, pair up in what are known as Cooper pairs. The pairing emerges from quantum mechanics itself, mediated by the vibrations of the lattice. Once paired, the electrons move in perfect synchrony, encountering no resistance. The randomness of individual scattering events is transformed into the collective order of superconductivity, where currents can flow without loss. This phenomenon, observed first in Mercury in 1911 by Heike Kamerlingh-Onnes, remains one of the most remarkable examples of order born from noise. Statistical mechanics provides the framework for understanding these transformations. By treating randomness as fundamental, it reveals how large-scale laws emerge. The temperature of a gas, for example, is not the energy of any one molecule, but the average of billions. Pressure is not a property of a single particle, but the collective effect of countless collisions. Even though each particle moves unpredictably, the ensemble obeys strict laws. The mathematics of probability turns apparent chaos into reliable regularity. The role of randomness in creating order is equally evident in chemical reactions. In solution, molecules move erratically, colliding in ways that seem accidental. Yet these random encounters allow them to overcome energy barriers, forming bonds that give rise to new substances. In the primordial soup of early Earth, such stochastic collisions may have produced the first self-replicating molecules, setting the stage for life. Random motion, filtered through the constraints of chemistry, can yield structures of astonishing complexity. Order emerging from randomness also appears in far larger systems. The clustering of galaxies in the universe traces its origins to tiny fluctuations in the density of matter shortly after the Big Bang. These fluctuations, themselves the result of quantum noise magnified during inflation, grew under the influence of gravity into the cosmic web of filaments and voids observed today. The vast structures of the cosmos are, in this sense, fossilized imprints of randomness. At every scale, from molecules to galaxies, noise has proven to be not an obstacle, but a seed. When conditions are right, fluctuations amplify into patterns. Randomness condenses into order. The paradox is profound. What seems chaotic at one level becomes law-like at another. The lesson is that noise is not the negation of structure, but the material out of which structure is made. In biology, the principle of order arising from randomness takes on its most extraordinary form. At the molecular level, mutations occur with no regard for outcome. A change in DNA may substitute one base for another, delete a section, or duplicate a gene. These events are stochastic, driven by chemical instabilities, radiation, or errors in replication. Most mutations are neutral, some are harmful, and a few prove advantageous. Natural selection acts on this pool of chance, amplifying the beneficial variations and discarding the harmful. Over millions of years, this process has sculpted the diversity of life. The eyes that perceive light, the wings that lift birds into the sky, the complex neural circuits of human brains, all are products of randomness, filtered through survival. Without noise at the genetic level, evolution would have no raw material to work upon. This principle extends into ecosystems, where the interaction of countless individuals, each with unpredictable behavior, produces large-scale stability. A predator may succeed or fail in a hunt. A seed may sprout or perish. A storm may alter the landscape. Yet out of this unpredictability, populations settle into balances, food chains stabilize, and ecosystems endure for centuries. The apparent chaos of life at the individual level generates order at the collective level, much as molecules in motion produce stable pressure and temperature. The nervous system demonstrates another way randomness can become a tool rather than a hindrance. Neurons communicate with electrical pulses, but the timing of these pulses is not perfectly regular. There is variability, noise, in the firing patterns. Far from being a defect, This variability can sharpen perception. In a process called stochastic resonance, the presence of noise allows a weak signal to cross the threshold of detection, making it perceptible when it would otherwise be lost. Experiments have shown that certain levels of random input can improve the sensitivity of sensory systems, from detecting faint vibrations in mechanoreceptors to perceiving subtle sounds. The brain, rather than suppressing noise, sometimes relies on it. Even in the realm of cognition, randomness plays a role. Creativity often depends on the ability to generate novel associations, to move beyond predictable patterns of thought. Noise in neural circuits may provide the variability needed for such leaps, allowing the mind to explore possibilities rather than remain fixed on rigid pathways. Decision-making, too, benefits from stochasticity, preventing organisms from becoming trapped in repetitive behaviors. In this way, noise is not only tolerated but actively integrated into the functioning of life. From genetic variation to neural dynamics, from ecosystems to evolution, biology demonstrates that randomness is not the opposite of order, but its wellspring. The structures of life emerge not from deterministic blueprints, but from a continuous interplay between chance and law, between mutation and selection, between variability and stability. Life is not fragile in the face of noise. It is built upon it. As physics, chemistry, and biology converge on this truth, a deeper picture of reality emerges. The universe is not a silent machine running on fixed rails. It is a creative process in which noise and order dance together, each giving rise to the other. The stability of matter, the complexity of life, the structure of galaxies all owe their existence to fluctuations that once seemed meaningless. With this recognition, the journey turns inward. If noise can give rise to order in atoms and ecosystems, what role does it play within the human brain? How does randomness shape thought, perception, and creativity? The next chapter explores these questions, revealing that the mind itself may depend on noise in ways as profound as the cosmos. The human brain is often described as the most complex structure in the known universe. It contains billions of neurons, each connected to thousands of others, forming a network of staggering intricacy. For centuries, scientists imagined this network as a kind of machine, deterministic in its operation, with thoughts and perceptions arising from precise patterns of electrical activity. Yet as our understanding of neuroscience deepened, another truth emerged. The brain is not a perfectly ordered mechanism. It is noisy. Its neurons fire with variability, its circuits fluctuate, and its rhythms are laced with randomness. Far from undermining its function, this noise appears to be essential to how the brain works. Neurons communicate by firing action potentials, brief spikes of voltage that travel along their axons and release neurotransmitters at synapses. Early models treated this firing as predictable, like the clicks of a telegraph key. But detailed measurements revealed that the timing of spikes is not exact. Present the same stimulus to a neuron repeatedly, and its responses will vary. Sometimes it fires sooner, sometimes later, sometimes not at all. The nervous system operates against a backdrop of uncertainty. This variability is not simply noise imposed from the outside. It arises from the stochastic behavior of ion channels in the neuron's membrane. These microscopic pores open and close randomly, allowing sodium and potassium ions to flow and generate electrical signals. Even at rest, these channels flicker unpredictably, introducing fluctuations into the neuron's voltage. At the level of molecular machinery, randomness is inescapable. Yet instead of degrading information, the brain seems to make use of this variability. One of the most striking examples is stochastic resonance. In physics, this phenomenon occurs when the presence of noise allows a weak signal to be detected that would otherwise fall below threshold. In biology, similar effects have been observed in sensory systems. Experiments have shown that a faint tactile stimulus, too weak to be felt, becomes detectable when a small amount of random vibration is added. The noise effectively boosts the signal into awareness. In the auditory system too, certain levels of background noise can improve the detection of faint tones. These findings suggest that the brain exploits noise to sharpen perception, turning randomness into a tool. Beyond perception, Randomness appears in the brain's higher functions. Decision-making, for instance, does not always follow deterministic pathways. Faced with choices, the nervous system exhibits variability in how it accumulates evidence and arrives at conclusions. This stochasticity may prevent rigid, predictable responses, allowing flexibility and adaptability in a changing environment. Creativity, too, may draw on the brain's noisy dynamics. By introducing variability into neural activity, noise provides the raw material for novel associations and unexpected insights. It prevents thought from becoming locked into repetitive loops, opening space for exploration. At first, the presence of noise in such a finely tuned system may seem surprising, but when seen through the lens of physics and biology, it fits into a larger pattern. Just as randomness in genetics fuels evolution, and fluctuations in physics give rise to stability, so too does noise in the brain enable perception, adaptability, and innovation. The nervous system is not a deterministic clockwork but a stochastic engine, harnessing uncertainty to produce meaning. The question then arises, does quantum noise itself play a role in the brain, or is the variability we observe merely the result of classical processes? Some researchers have explored this possibility, pointing to evidence that certain biological systems may exploit quantum effects. Photosynthesis, for example, seems to use quantum coherence to transfer energy efficiently. The magnetic sense of birds may rely on quantum entanglement in cryptochrome proteins. These examples show that biology is capable of operating at the quantum edge. Whether the brain itself makes direct use of quantum processes remains an open question. What is clear is that, at the very least, classical noise derived from molecular and cellular processes is central to neural function. The presence of noise in the brain is therefore not a defect, but a feature. It ensures sensitivity, adaptability, and creativity. It reminds us that even the most complex forms of order, including thought itself, depend on fluctuations at their foundations. The mind is not a fortress against noise. It is a structure built upon it, a living testament to the power of randomness to generate meaning. The role of noise in perception becomes even clearer when scientists look at how the nervous system processes signals under real-world conditions. Sensory organs are constantly bombarded by stimuli, many of them faint or ambiguous. A touch on the skin, the rustle of leaves, a faint scent carried on the wind. These signals are often buried beneath competing inputs and internal fluctuations. Yet humans and other animals can detect them with remarkable sensitivity. This paradox is explained in part by the presence of noise. In controlled experiments, weak stimuli that are ordinarily below the threshold of detection become perceivable when a certain level of random noise is introduced. In the somatosensory system, for example, researchers have shown that adding a small vibration to the skin improves the detection of faint touches. The same principle applies in the auditory system, where background noise at specific levels helps subjects identify quiet tones. The effect is known as stochastic resonance. It reveals that the brain does not simply tolerate noise, it incorporates it into its own processing, using fluctuations to amplify weak signals. This beneficial role of noise extends beyond basic perception. The brain relies on variability to maintain flexibility in decision-making. When confronted with choices, neural circuits accumulate evidence from the environment, integrating signals over time. Yet the decision process is not purely deterministic. Randomness enters as neurons fluctuate in their firing, producing variability in response times and outcomes. This variability prevents the system from becoming rigid. In uncertain environments, such stochasticity may confer an evolutionary advantage, allowing organisms to explore different strategies rather than becoming trapped in predictable patterns. Memory, too, is touched by randomness. The process of storing and recalling information is not flawless, and variability plays a part in both its fragility and its resilience. On the one hand, noise in synaptic transmission introduces imperfections, leading to distortions in recall. On the other, this same variability allows memories to generalize, to connect across different contexts, rather than remaining tied to rigid patterns. In this sense, noise supports the creative blending of experiences, giving memory a generative quality that strict determinism could never provide. Creativity itself may depend on the brain's noisy dynamics. To generate new ideas, the mind must escape the predictable associations of the familiar. Random fluctuations in neural activity introduce novel combinations, unexpected connections between concepts. While not all such connections are useful, some provide the spark of innovation. Many studies of creative problem-solving show that moments of insight often arise after periods of diffuse, less directed thought, a state in which noise can wander through the mental landscape, linking ideas in unforeseen ways. The variability of the brain thus becomes the soil of imagination. The question of whether quantum noise directly influences the brain remains unsettled. Certain biological systems provide intriguing precedents. In photosynthesis, experiments have revealed that energy transfer within light harvesting complexes occurs with near-perfect efficiency, a process best explained by quantum coherence. In avian magnetoreception, some birds appear able to sense Earth's magnetic field through cryptochrome proteins in their eyes, a mechanism that may rely on quantum entanglement. These cases suggest that biological systems can indeed exploit quantum effects when conditions allow. Whether the brain operates in a similar way is debated. The warm, wet environment of neural tissue seems inhospitable to maintaining delicate quantum states, which usually require isolation from noise to persist. Nonetheless, research continues, exploring whether phenomena like microtubule dynamics or electron tunneling in proteins could sustain quantum processes relevant to cognition. For now, the evidence is limited, and most neuroscientists attribute the variability of brain function to classical noise arising from ion channels, synapses, and network dynamics. Yet the possibility remains open, and it continues to inspire inquiry at the boundaries of physics and biology. What is certain is that the brain embraces noise rather than eliminating it. From the firing of neurons to the perception of faint signals, from the flexibility of decision-making to the generative power of creativity, randomness plays a constructive role. It ensures that human thought is not locked into predetermined tracks, but capable of adaptation, discovery, and imagination. Noise is not an obstacle to cognition. It is woven into its essence. The realization that noise is essential to brain function has also highlighted the limits of scientific knowledge. While experiments show how variability in neural firing, synaptic transmission, and sensory processing contributes to perception and decision-making, the deeper question of how consciousness itself arises remains open. Some have speculated that quantum effects might play a role, pointing to the apparent mystery of subjective experience and the complexity of the brain. Proposals such as quantum consciousness suggest that entanglement or superposition could be fundamental to awareness. Yet when examined against the standards of evidence, these claims remain unproven. The delicate nature of quantum states makes them difficult to sustain in the warm and noisy environment of living cells. Decoherence, the process by which quantum superpositions collapse through interaction with the environment, occurs on timescales far shorter than those relevant to neural processing. Most neuroscientists therefore conclude that classical noise arising from molecular and cellular processes is sufficient to explain the variability of brain function. Consciousness, while still not fully understood, does not require invoking unverified quantum mechanisms. This distinction is crucial. Science progresses by drawing a clear line between what is known, what is plausible, and what remains speculative. It is established that stochastic resonance sharpens perception, that variability in neural firing aids decision-making, and that noise contributes to creativity and memory. It is plausible that biology in some cases uses quantum effects, as seen in photosynthesis and magnetoreception. It remains speculative to suggest that the brain harnesses quantum processes to generate consciousness. Keeping these boundaries clear preserves both the integrity of neuroscience and the openness of inquiry. Even without quantum explanations, the constructive role of noise in the brain is profound. It allows for flexibility in behavior, prevents thought from becoming rigid, and ensures adaptability in uncertain environments. The variability of neural responses, once seen as a flaw in measurement, has become recognized as a feature of the system itself. It is the nervous system's way of embracing the uncertainty inherent in reality. The same fluctuations that make ion channels open unpredictably or synapses release neurotransmitters with varying probability are the fluctuations that enable perception, learning, and creativity. In this sense, the brain mirrors the universe it inhabits. Just as atoms are stabilized by uncertainty, just as galaxies emerge from quantum fluctuations in the early cosmos, so too does the mind find its form in the presence of noise. Thought itself may be the highest expression of the principle that order arises not from silence, but from randomness, the variability of neurons, the noise in perception, the stochasticity of decision-making. These are not imperfections, but the essence of cognition. As neuroscience advances, researchers continue to probe the ways in which the brain uses noise. They build models of networks that incorporate randomness, test how variability influences learning, and develop technologies like brain-computer interfaces that must contend with noisy signals. Each step reinforces the truth that randomness is inseparable from thought. Thus, the chapter closes with a reflection on the paradox at the heart of the brain. It is the most intricate organ known, capable of abstract reasoning, language, and imagination. Yet, it depends on fluctuations at the level of molecules and ions. Noise, rather than degrading its performance, empowers it. Consciousness may remain a mystery, but the role of randomness in perception, creativity, and decision-making is clear. The mind, like the cosmos, is built not on certainty but on possibility. For most of human history, noise was something to be avoided. Engineers sought to suppress it in machines, musicians tried to silence it in instruments, and scientists worked to reduce it in experiments. Yet in the 20th and 21st centuries, a remarkable transformation occurred. What once seemed like interference became a resource. Instead of fighting noise, humans began to harness it, especially the noise that arises from quantum mechanics. The same fluctuations that limit certainty in measurement now serve as the foundation for some of the most advanced technologies ever built. Electronics provides the clearest example of this shift. Every transistor, the fundamental switch of modern computing, operates in an environment filled with noise. Electrons do not flow smoothly like water through a pipe. They hop across barriers, scatter off impurities, and tunnel through regions where classical physics says they should not pass. At small scales, this randomness becomes unavoidable. In the early days of electronics, engineers treated it as a nuisance, something to be minimized through design. But as devices shrank to the scale of nanometers, quantum noise revealed itself as an intrinsic part of operation. Modern microchips, with billions of transistors etched onto their surfaces, function not in spite of these fluctuations, but in dialogue with them. Quantum tunneling, once a theoretical oddity, is now a practical necessity. In flash memory devices, electrons tunnel through insulating barriers to store data. In scanning tunneling microscopes, the very act of imaging atoms depends on measuring the tiny tunneling currents that fluctuate between a tip and a surface. What was once considered noise has become a signal in its own right, a measurable phenomenon used to reveal structure at the atomic scale. Beyond electronics, randomness itself has been turned into a resource for security. Cryptography, the science of encoding information, depends on random numbers to generate keys that cannot be guessed. Traditional computers rely on algorithms to produce pseudo-random numbers, but these are ultimately deterministic and vulnerable to attack if the algorithm is known. Quantum random number generators solve this problem by drawing directly on quantum noise. The detection of a photon at one detector or another, the precise moment an atom decays, the unpredictable path of an electron tunneling across a barrier, these outcomes are guaranteed by physics to be random. No hidden pattern can predict them, making them ideal for securing communications in an age of digital threats. Quantum key distribution pushes this principle further. In protocols such as BB84, information about encryption keys is transmitted using single photons. Because of the uncertainty principle, any attempt by an eavesdropper to measure these photons introduces detectable noise. The presence of this noise reveals interception, ensuring that only the intended parties share the secret key. Quantum cryptography does not merely use noise as a resource. It transforms it into a shield, turning the unpredictability of the universe into the basis of trust. Perhaps the most ambitious attempt to harness quantum fluctuations is the quest for quantum computing. Classical computers process bits that are either 0 or 1. Quantum computers process qubits that can exist in superpositions of 0 and 1, entangled with one another in ways that classical physics cannot match. Maintaining these fragile states requires shielding from environmental noise, but paradoxically, it is the same quantum uncertainty that gives qubits their power. Superposition allows them to explore many possibilities simultaneously, and entanglement links their fates across distance. What was once seen as randomness becomes computational parallelism, a new resource for solving problems beyond the reach of classical machines. The shift from resisting noise to embracing it marks a profound change in human ingenuity. Technology has reached a point where the fundamental fluctuations of nature are not obstacles but allies. The hiss of quantum uncertainty, once feared as the limit of knowledge, now drives innovation in fields, from secure communication to advanced computing. Humanity has learned to engineer with uncertainty rather than against it, to turn the restlessness of the quantum world into the raw material of progress. As technology advanced, engineers learned not only to tolerate quantum noise, but to design systems that depend upon it. One striking example is in detectors and sensors, where sensitivity is often pushed to the very limits of physics. Photodetectors that measure single photons rely on the probabilistic arrival of light quanta. Avalanche photodiodes, superconducting nanowire detectors, and other devices count photons one by one, each detection a product of quantum randomness. These instruments are essential for fields as diverse as astronomy, medical imaging, and quantum communication. Without harnessing noise at the quantum level, the faintest signals from distant galaxies or subtle changes in biological tissues would remain invisible. In radio astronomy, scientists listen to the faintest whispers of the cosmos, signals so weak they are easily drowned in thermal noise. To extract meaning, they cool detectors to temperatures near absolute zero, reducing classical noise and leaving only the quantum fluctuations that cannot be removed. Even then, noise remains the limiting factor. Yet by modeling it, by learning its statistics, astronomers transform noise into information, teasing out cosmic microwave background radiation or the pulses of distant neutron stars. Another field where quantum noise is both a challenge and a tool is precision measurement. Gravitational wave detectors such as LIGO measure ripples in space-time produced by colliding black holes or neutron stars. These detectors are so sensitive that quantum fluctuations in the photons of their laser beams limit their accuracy. Engineers combat this with techniques like squeezed light, in which the uncertainty of one property of light is reduced at the expense of another, effectively shaping quantum noise to the needs of the experiment. This approach has already improved detection sensitivity, allowing humans to hear the faint tremors of the universe. The very noise that seemed like an obstacle becomes part of the strategy. Quantum sensing takes the principle further. Systems based on nitrogen vacancy, centers in diamonds, exploit quantum spin states to detect tiny magnetic and electric fields with extraordinary precision. Atomic clocks, which rely on the quantum transitions of atoms like cesium or strontium, achieve accuracies so high that they would lose less than a second over the age of the universe. These clocks function at the edge of quantum uncertainty, their precision arising from measuring transitions that are inherently probabilistic. In all these cases, noise is not eliminated but transformed into a reference, a guide to greater accuracy. In electronics, thermal and quantum fluctuations are omnipresent. Johnson noise, discovered in the 1920s, arises from the random motion of electrons in resistors. Shot noise, another form, comes from the discrete nature of electric charge as current flows. These noises once limited the performance of amplifiers and circuits. Today they are carefully characterized, used as diagnostic tools, and even exploited in applications like secure key generation. Engineers design circuits that take advantage of noise's statistical properties rather than fighting an impossible battle to silence it. Even in emerging areas like quantum simulation and quantum computing, managing noise is not only a technical hurdle, but also a design principle. Qubits are extraordinarily fragile, collapsing when disturbed by their environment. Yet, through techniques such as quantum error correction, engineers use redundancy to counteract noise. Paradoxically, it is the same theory of information that once defined noise as a limit that now provides the tools to turn it into a manageable partner. The effort to build practical quantum computers is, at its heart, the effort to understand and channel quantum noise. Step by step, the history of technology reveals a transformation. Noise, once regarded as interference to be suppressed, is now treated as a fundamental reality to be harnessed. Whether in detectors that count single photons, clocks that mark the passage of time with atomic precision, or instruments that listen to the faintest tremors of the cosmos, quantum fluctuations are no longer background static. They are central players in the ongoing dialogue between human ingenuity and the restless universe. The history of science and engineering is often told as a story of overcoming noise, of building instruments ever more precise, machines ever more predictable. Yet as technology reached the scale of atoms and photons, this story changed. Instead of suppressing noise, engineers learned to live with it, to shape it, and finally, to exploit it. The philosophical shift is as important as the technical one. It reflects a new understanding that uncertainty is not the opposite of control, but a deeper kind of resource, a force that can be directed toward useful ends. This change is visible across the spectrum of modern technologies. In communication systems, randomness ensures security. In detectors, quantum fluctuations mark the ultimate limit of sensitivity, but they also provide the signals by which faint phenomena can be recognized. In quantum computing, the very fragility of superpositions and entanglement is both a challenge and a source of unprecedented computational power. Instead of treating uncertainty as a flaw, engineers now view it as the defining character of the quantum world, and they design accordingly. The embrace of noise also alters the way humans think about progress. In earlier centuries, progress meant reducing variability, smoothing the irregularities of nature into predictable laws and reliable machines. In the quantum age, progress means something subtler, understanding how fluctuations work, and finding ways to incorporate them into design. The transition from analog electronics to digital systems illustrated this point. Digital circuits thrive because they tolerate a degree of noise, interpreting signals as zeros or ones, despite fluctuations. At the quantum level, this principle deepens, with systems built to operate not in spite of noise, but through it. Looking ahead, the ability to harness quantum noise promises technologies that were once science fiction. Secure communication networks based on quantum key distribution are already in development, creating channels that cannot be intercepted without detection. Quantum computers, though still in their infancy, aim to solve problems in chemistry, materials, and optimization, far beyond the reach of classical machines. Quantum sensors promise to map brain activity, monitor Earth's magnetic field, and detect underground structures with unprecedented resolution. Each of these advances depends not on escaping noise, but on mastering it. The philosophical lesson is clear. Humans no longer stand apart from the uncertainty of the universe, striving to silence it. They have learned to build with it, to make uncertainty part of the blueprint. This does not mean abandoning the pursuit of accuracy or control. It means recognizing that accuracy itself emerges from an intimate relationship with noise. The clearest signals are those shaped by an understanding of their background. The most precise measurements are those that account for irreducible fluctuations. The most powerful computers may be those that embody uncertainty in their very logic. In this way, technology mirrors the lesson of physics itself. Quantum mechanics taught that reality is not deterministic clockwork, but probability unfolding. Modern engineering reflects this truth, turning uncertainty into capability. From the circuits in a smartphone to the instruments listening to the universe, humanity has reached a point where noise is no longer a hindrance, but a partner. The story of noise and technology thus prepares us for the broader implications. If humans can build machines that thrive on uncertainty, what does this say about the nature of the universe itself? Does randomness undermine meaning, or does it provide the very foundation for order and knowledge? The next chapter turns to philosophy, exploring how a noisy universe challenges our ideas of determinism, free will, and the interpretation of probability itself. For centuries, philosophers and scientists debated whether the universe was ultimately deterministic or indeterministic, whether every event was the inevitable consequence of those before it, or whether chance played a fundamental role. The rise of classical physics seemed to settle the matter in favor of determinism. Newton's laws, precise and predictable, suggested that if one knew the position and momentum of every particle in the universe, one could calculate its entire future. Pierre-Simon Laplace famously imagined a vast intellect, later called Laplace's demon, that could see all of reality at once and predict every outcome. In this vision, the universe was a clockwork, with no room for genuine uncertainty. The birth of quantum mechanics shattered this view. At the smallest scales, probability replaced certainty. The decay of a single radioactive atom, the arrival of a photon at one detector or another, the precise outcome of a measurement, all were irreducibly unpredictable. It was not a matter of hidden details waiting to be uncovered. Experiments confirmed that no local hidden variables could explain the results. The world was not a clockwork after all, but a tapestry woven of probabilities. Determinism, at least in its classical form, could no longer stand as the whole picture. This discovery forced philosophy to grapple with new questions. What does it mean for the universe to be indeterministic? Does randomness undermine causality, or does it reveal a deeper order hidden in probability itself? Some physicists embraced the idea that chance is fundamental, that nature does indeed roll dice. Others sought interpretations of quantum mechanics that would preserve determinism, even if at the cost of introducing strange concepts such as multiple universes. The Copenhagen interpretation, championed by Niels Bohr, insisted that physics should describe only what can be observed and measured. In this view, asking about the reality of an electron's position before measurement was meaningless. Probability was not ignorance, but the best description possible. The act of measurement was fundamental, collapsing possibilities into outcomes. Philosophically, this interpretation leaned toward indeterminism, accepting noise as an intrinsic feature of reality. Albert Einstein resisted this conclusion, believing that quantum mechanics was incomplete. He argued that there must be hidden variables, deeper laws that would restore determinism. His debates with Bohr, especially at the Solvay conferences, became legendary, echoing through the history of science. Yet experiments inspired by John Bell in the 1960s, and refined with increasing precision ever since, have consistently shown that no local hidden variable theory can reproduce the predictions of quantum mechanics. The evidence points strongly toward irreducible indeterminism at the core of nature. Other interpretations sought to escape this dichotomy. Hugh Everett's many worlds interpretation proposed that all possible outcomes of a quantum event actually occur, each in its own branch of a vast multiverse. In this picture, determinism survives, but only if one accepts an infinity of parallel realities. Relational quantum mechanics and other modern interpretations suggest that reality is not absolute but relative, that properties exist only in relation to other systems. Each of these views reflects different philosophical commitments, yet all grapple with the same truth. Quantum noise cannot be dismissed. It must be integrated into the very fabric of reality. The implications reach beyond physics into questions of free will and human meaning. If the universe is deterministic, then every thought and action is predetermined, the inevitable unfolding of initial conditions. If the universe is indeterministic, randomness enters the picture. But does randomness equate to freedom? Does a noisy universe make space for human choice? Or does it simply replace necessity with chance? These are not questions physics can answer fully, but they are questions it forces us to ask. The noisy universe therefore reshapes some of the oldest debates in philosophy. It undermines the dream of absolute predictability, challenges classical notions of causality, and forces a reconsideration of how probability should be understood. Rather than being ignorance, probability may be the most fundamental description possible. Noise, far from being an imperfection, may be the defining character of reality. Probability is one of the most unsettling aspects of quantum mechanics because it challenges the way humans normally think about cause and effect. In daily life, probability usually reflects ignorance. If a coin is flipped, one might say there is a 50% chance of heads. But in principle, if every detail of the coin's motion, the air currents, and the force of the flip were known, the outcome could be calculated. The probability is only a measure of limited knowledge. In quantum mechanics, however, probability has a deeper status. Even with complete knowledge of a system's wave function, the outcome of a single measurement is uncertain. The best that can be said is that some results are more likely than others. Probability is not ignorance. It is reality itself. This shift forces philosophy to reconsider what it means for an event to occur. The decay of a radioactive atom is not caused by hidden factors waiting to be uncovered. It simply happens, guided only by statistical laws. The half-life of uranium, for example, is a reliable constant, but which atom decays, at which moment, is unpredictable. The universe thus presents a mixture of law and chance. Laws determine the probabilities, but chance decides the outcomes. Reality is a partnership between necessity and noise. Different interpretations of quantum mechanics offer different ways of making sense of this. In the Copenhagen view, the wave function describes probabilities that collapse into outcomes upon measurement. In many worlds, all outcomes occur, and probability reflects the branching of realities. In objective collapse theories, wave functions spontaneously reduce without observation, introducing randomness as a physical process. Each interpretation has strengths and weaknesses, but none eliminates noise. Whether as branching, collapse, or fundamental indeterminism, uncertainty remains central. This indeterminism has profound consequences for the philosophy of causality. In classical physics, every event has a determinate cause. In quantum physics, causes are probabilistic. One can say that a radioactive nucleus has a 50% chance of decaying in a given interval, but not why one atom decays now and another later. This raises the question of whether causality itself is a human construct, a way of describing patterns, rather than a fundamental feature of reality. If so, noise is not the breakdown of causality but its foundation, the texture upon which patterns emerge. The human search for meaning has always been tied to predictability. Ancient myths often portrayed the universe as ordered by gods or fate, narratives that made the world comprehensible. Classical science replaced these with natural laws, equally predictable and secure. Quantum mechanics replaced certainty with probability, undermining both myth and classical determinism. It left humans in a universe where noise is not an intruder, but a native element. This is not the comfortable order of Newton's cosmos, but something stranger, where the deepest truths are expressed in terms of chance. For some, this is unsettling. It suggests a universe without final control, where randomness is inescapable. For others, it is liberating. It allows for novelty, for events not entirely predetermined, for a cosmos in which genuine possibility exists. Physics does not provide the final word on meaning, but it frames the debate in a new way. A noisy universe is one in which certainty is replaced by openness, inevitability by possibility. As the implications of this worldview unfold, the question arises of how humans should live with noise as the foundation of reality. If randomness permeates the universe, what becomes of freedom, purpose, and responsibility? These questions extend beyond the laboratory into philosophy, ethics, and daily life. The exploration of a noisy universe thus continues, not only in physics but in every human attempt to understand existence. The debate over free will has always been entangled with the question of determinism. If every action is the inevitable consequence of prior causes, then freedom may be an illusion. Classical physics seem to support this conclusion. In a Newtonian universe, The future was written in the past, and every thought, choice, and movement of the human body was predetermined by the positions and velocities of particles. When quantum mechanics revealed the presence of indeterminism, some hoped it would rescue free will. But the relationship between randomness and freedom is more complex than it first appears. Randomness alone does not constitute freedom. If human actions were dictated solely by chance, then responsibility and intention would vanish. A choice that emerges from pure noise is no more free than a choice predetermined by mechanical necessity. True freedom, if it exists, must lie somewhere between determinism and randomness, shaped by but not reduced to either. What physics reveals is that the foundations of the universe contain both elements. Laws govern probabilities, while outcomes retain uncertainty. This structure may provide the space in which human agency operates, though science cannot define its boundaries. Philosophers and scientists who confront this issue often draw a careful line between what physics can establish and what remains the domain of interpretation. Physics can show that determinism in the classical sense is untenable, that noise is built into the structure of reality. It can demonstrate that probability is irreducible, not merely ignorance, but it cannot say whether this opens the door to free will in the human sense. That question belongs as much to philosophy as to science. What can be said with confidence is that a noisy universe is not devoid of meaning. Noise, far from undermining significance, provides the conditions for complexity and novelty. Without randomness, there would be no evolution, no creativity, no emergence of new structures. A universe of perfect determinism would be frozen in inevitability, with every event scripted in advance. A universe of pure randomness would dissolve into chaos without pattern. The noisy universe we inhabit stands between these extremes. It is a place where order and chance intertwine, where patterns arise from fluctuations, where stability and unpredictability coexist. The philosophical implications of this view are profound. It calls into question the dream of total knowledge, the belief that reality can be reduced to absolute certainty. It replaces that dream with something richer, a recognition that uncertainty is woven into the fabric of existence. It suggests that meaning is not erased by noise but created within it, that the unpredictability of the universe is not a defect, but a gift. Thus, the philosophical journey mirrors the scientific one. From determinism to probability, from certainty to openness, humanity has been compelled to rethink its place in the cosmos. Quantum noise is not only a feature of equations, it is a challenge to our understanding of causality, freedom, and meaning. It tells us that the universe is not a machine, but a process, a living interplay of order and chance. The next step in this exploration leads outward, beyond philosophy into cosmology. For if noise is written into the foundations of matter, what role has it played in shaping the largest structures of the universe? The following chapter turns to the cosmos itself, where quantum fluctuations in the earliest moments of time seeded galaxies, stars, and the vast web of matter that spans the heavens. When physicists turned their gaze from the microscopic world of particles to the vast scale of the universe, they discovered that the same quantum noise-shaping atoms also left its fingerprints on the cosmos itself. The story of galaxies, stars, and planets is not only one of gravity and matter, but also one of fluctuations magnified across unimaginable distances. The largest structures in existence can be traced back to the tiniest uncertainties at the dawn of time. According to modern cosmology, the universe began around 13.8 billion years ago in an event known as the Big Bang. In its earliest moments, it was unimaginably hot and dense, a seething plasma of particles and radiation. For decades, scientists struggled to explain how this universe could evolve into the structured cosmos we see today, filled with galaxies and clusters, rather than a perfectly smooth distribution of matter. The answer emerged from the theory of cosmic inflation, proposed in the early 1980s. Inflation suggested that in a fraction of a second after the Big Bang, the universe expanded exponentially, stretching space faster than the speed of light. During this inflationary epoch, quantum fluctuations that normally exist only at subatomic scales were blown up to cosmic proportions. Tiny variations in energy density, born from the uncertainty principle itself, were frozen into the fabric of space-time, as inflation drove the universe outward. What would have been fleeting ripples in a vacuum became the seeds of galaxies. In this way, noise at the smallest scales was written into the blueprint of the cosmos. Evidence for this remarkable process lies in the cosmic microwave background, the faint afterglow of the Big Bang that still fills the sky. First discovered in 1965 by Arno Penzias and Robert Wilson, this radiation is a nearly uniform bath of microwaves that has traveled for more than 13 billion years. Yet detailed measurements reveal slight anisotropies, tiny variations in temperature across the sky, at the level of 1 part in 100,000. These fluctuations match the statistical patterns predicted by quantum theory when applied to inflation. They are fossilized traces of quantum noise from the birth of the universe. Satellites such as COBE in the 1990s, WMAP in the early 2000s, and Planck in the 2010s mapped these anisotropies with increasing precision. The results showed a striking consistency with inflationary models. The spectrum of fluctuations, their scale dependence, and their statistical distribution all pointed to the same conclusion. The universe we inhabit, with its clusters of galaxies and cosmic filaments, arose from microscopic uncertainty stretched to astronomical scales. The largest order in existence is the child of the smallest randomness. This idea is more than a poetic metaphor. It is supported by rigorous mathematics and observational data. Inflation explains why the universe appears flat on large scales, why regions of the cosmos far apart in space share the same temperature, and why there are no exotic relics that would have dominated a non-inflationary universe. The theory does not just fit the data, it solves puzzles that had long troubled cosmology. And at its heart is quantum noise, fluctuations that could never be erased, only amplified. Thus, the same uncertainty that shapes the decay of atoms and the firing of neurons also shaped the galaxies themselves. Quantum mechanics, born in the study of the smallest scales, finds its ultimate expression in the architecture of the cosmos. The night sky, filled with stars and galaxies, is a vast map of quantum fluctuations written across billions of light years. The cosmic microwave background is often described as the most important photograph ever taken, a snapshot of the universe when it was only about 380,000 years old. At that time, the hot plasma of electrons and protons cooled enough for atoms to form, allowing light to travel freely through space. The radiation released in that moment still bathes the universe, stretched into microwave wavelengths by billions of years of cosmic expansion. When scientists measure its temperature across the sky, they find it astonishingly uniform, around 2.73 Kelvin. Yet upon closer inspection, the tiny variations in temperature reveal the fingerprints of quantum noise frozen into place during inflation. These fluctuations, measured at 1 part in 100,000, may seem insignificant, but gravity amplified them over cosmic time. Regions that began slightly denser than average attracted more matter, growing into the galaxies and clusters we see today. Regions slightly less dense became the great voids that stretch across millions of light years. The universe's vast cosmic web, with its filaments, clusters, and emptiness, is the large-scale echo of microscopic uncertainty. Noise at the quantum level became the architecture of the heavens. The first satellite to detect these variations was the Cosmic Background Explorer, or COBE, launched in 1989. Its instruments revealed both the near-perfect blackbody spectrum of the background radiation and the faint anisotropies predicted by inflation. The discovery earned John Mather and George Smoot the Nobel Prize in Physics in 2006. COBE showed that the Big Bang was not only hot and dense, but also seeded with fluctuations that would shape all future structure. A decade later, the Wilkinson Microwave Anisotropy Probe, or WMAP, provided a sharper map. From 2001 to 2010, WMAP measured the anisotropies with unprecedented detail, producing a picture of the infant universe that allowed scientists to determine its age, composition, and geometry with remarkable precision. The data showed that ordinary matter makes up less than 5% of the universe, dark matter about 25%, and dark energy about 70%. Beyond these revelations, WMAP confirmed the inflationary origin of cosmic structures by matching the predicted power spectrum of fluctuations. The most detailed measurements came with the Planck satellite, launched by the European Space Agency in 2009. Planck mapped the microwave background with such accuracy that it could detect subtle variations in the polarization of the light, further confirming the inflationary model. Its results pinned down the universe's age at 13.8 billion years and provided the clearest evidence yet that quantum fluctuations magnified by inflation seeded the cosmos. The anisotropies observed by Planck are not random noise in the colloquial sense. They are structured noise, following the precise statistical patterns predicted by quantum theory. Observations beyond the cosmic microwave background reinforce this picture. The distribution of galaxies across the sky, mapped by large surveys, reveals a pattern known as baryon-acoustic oscillations, ripples, that originated as sound waves in the early plasma. These ripples, imprinted on the distribution of matter, align with the fluctuations seen in the microwave background. The agreement across scales and epochs is striking. From the earliest light to the present cosmos, the fingerprints of quantum noise persist. Even the most distant galaxies observed by the James Webb Space Telescope provide glimpses of this story. Their distribution and clustering reflect the same initial conditions written into the cosmic background. Quantum fluctuations, stretched by inflation, became the seeds of stars, galaxies, and ultimately, of the conditions for life. The light from those galaxies, reaching us after billions of years, carries the silent testimony that noise is not the enemy of order, but its source. The recognition that quantum fluctuations seeded the cosmos has transformed cosmology from speculation into precision science. No longer is the early universe a mystery hidden beyond reach. It is written across the sky in patterns of microwave light, measured by satellites, telescopes, and detectors of extraordinary sensitivity. Each new observation tightens the connection between microscopic uncertainty and macroscopic structure, confirming that the vast cosmic web is the fossilized imprint of quantum noise. The role of fluctuations did not end with inflation. Even today, quantum processes continue to shape the universe. In particle accelerators, vacuum fluctuations influence scattering events, echoing the same physics that once sculpted galaxies. In astrophysical observations, quantum limits define the precision with which astronomers can measure faint light from distant stars. In gravitational wave observatories, the hiss of quantum noise in laser photons marks the boundary of sensitivity. The cosmos is never silent. Its foundations remain restless, and the echoes of that restlessness ripple outward into every measurement. Cosmologists now look for even deeper traces of these fluctuations. One frontier is the search for primordial gravitational waves, ripples in space-time itself generated during inflation. If detected, they would provide direct evidence of quantum fluctuations in the gravitational field, revealing the link between quantum mechanics and general relativity. Instruments such as BICEP and future observatories aim to measure the polarization of the cosmic microwave background with enough precision to detect these faint signatures. The discovery would not only confirm inflation, but also open a window into physics at energies far beyond the reach of accelerators. Another frontier is the study of large-scale structure. Surveys mapping the positions of millions of galaxies allow scientists to test whether the statistical distribution of matter matches predictions from inflation. The remarkable agreement so far strengthens the case that randomness at quantum scales generated the order of the universe. Yet small discrepancies hint at new physics, perhaps involving dark matter or dark energy, whose nature remains elusive. The interplay of noise and structure continues to guide discovery. The James Webb Space Telescope, peering into the earliest epochs of galaxy formation, offers further evidence. Its observations reveal galaxies forming sooner and more abundantly than some models predicted, raising questions about how quantum seeds grew under the influence of gravity and cosmic expansion. Each new image from deep space is a reminder that the universe is a living record of fluctuations magnified into structures of breathtaking scale. Ultimately, the idea that galaxies, stars, and planets, and by extension, life itself emerged from quantum noise, carries profound implications. It links the smallest scales of physics to the largest scales of cosmology, uniting the behavior of subatomic particles with the destiny of the universe. The night sky, with its countless points of light, is a map of uncertainty transformed into order. Every galaxy is a monument to randomness. Every star, a testament to fluctuations that refuse to vanish. The chapter closes with a reflection on this astonishing truth. The cosmos is not the outcome of perfect design nor of pure chaos. It is the product of noise, structured by law, of uncertainty, guided by probability, of fluctuations sculpted by gravity. From the faint ripples of the microwave background to the spiral arms of galaxies, the universe speaks in the language of quantum noise. What once seemed like a limitation of knowledge is revealed as the foundation of existence. The next step in this journey turns inward once more, asking how humans live with fundamental uncertainty. If the cosmos itself is born from noise, how should people think about randomness in their own lives? The final chapter explores this question, tracing the role of uncertainty in science, risk, and meaning, and closing with the recognition that noise is not the absence of order, but the condition for complexity and life. From the restless vacuum of quantum fields to the galaxies seeded by fluctuations in the early universe, uncertainty lies at the heart of reality. Yet for humans, the challenge is not only to understand this uncertainty, but to live with it. The recognition that randomness is woven into existence raises questions that reach far beyond physics. How do people make choices in a world where outcomes can never be predicted with absolute certainty? How does science progress when its theories are built upon probabilities rather than certainties? And what does it mean, philosophically and practically, to live in a noisy universe? Humanity has always wrestled with randomness. Ancient civilizations read omens in the flight of birds or the roll of dice, seeking patterns in chaos. The development of probability theory in the 17th century marked a turning point, transforming uncertainty from superstition into mathematics. Figures like Blaise Pascal and Pierre de Fermat began to formalize the rules of chance while analyzing games of dice and cards. What began as an attempt to understand gambling became the foundation of a science of risk. Probability allowed humans to quantify uncertainty, to calculate odds, and to make informed decisions even when the outcome could not be known. This mathematical understanding grew into a central tool for science. Statistics became the language of uncertainty, enabling researchers to draw conclusions from incomplete data. Medicine relies on clinical trials that measure probabilities of success and failure. Climate science projects ranges of outcomes rather than precise predictions. Physics itself, in the wake of quantum mechanics, accepts that its laws govern probabilities rather than certainties. In every case, progress depends not on eliminating uncertainty, but on embracing it, on finding ways to work with noise rather than against it. In daily life, probability guides decisions large and small. Insurance, finance, and medicine all operate on the management of risk. A driver knows that while the chance of an accident on any given trip is small, the risk is real enough to warrant safety measures. An investor understands that markets fluctuate unpredictably, but uses probability to balance risk and reward. A doctor prescribes treatments not with guarantees, but with likelihoods of effectiveness. Modern society is built on the ability to navigate uncertainty. Science embodies this approach most deeply. Theories are never final truths, but models, tested by data, revised when anomalies arise. Quantum mechanics itself is an acknowledgement that certainty is beyond reach at the smallest scales. Yet its probabilistic laws are among the most precise ever devised, predicting experimental outcomes with accuracy to many decimal places. The acceptance of uncertainty does not weaken science. It strengthens it, making it flexible, self-correcting, and open to discovery. To live with uncertainty, then, is not to surrender to ignorance. It is to accept the universe as it is restless, probabilistic, and open. Just as physicists harness noise in technology, humans harness uncertainty in life, using probability to guide decisions, to reduce risk, and to cultivate resilience. Far from undermining meaning, randomness provides the texture of experience. Without uncertainty, every life would be predetermined, every outcome inevitable. It is uncertainty that makes choice, responsibility, and possibility real. Living with uncertainty means acknowledging that not all outcomes can be controlled, yet it also means discovering that unpredictability can be a source of strength. In science, as in life, noise is not only a barrier, but also a catalyst for discovery. Many of the most important breakthroughs have emerged not from perfect prediction, but from unexpected results. The discovery of cosmic microwave background radiation, for example, came when two engineers were trying to eliminate what they thought was noise from their radio antenna. The hiss they could not remove turned out to be the afterglow of the Big Bang. What first appeared as interference became one of the greatest discoveries in cosmology. In human affairs, unpredictability can similarly open new paths. A chance meeting may alter the course of a career. A random idea may spark a work of art. A mistake may lead to innovation. The history of creativity is filled with such serendipity, where noise in thought processes generates novelty. Just as genetic mutations provide the raw material for evolution, variability in human imagination fuels invention. A perfectly deterministic mind would repeat itself endlessly. A noisy mind produces new possibilities. Resilience, too, depends on recognizing uncertainty. Systems designed to withstand only one exact set of conditions are fragile. Those that can adapt to variability are robust. Nature demonstrates this truth everywhere. Ecosystems survive disturbances because they contain diversity, randomness in the traits and behaviors of their members. Human societies endure crises when they allow for flexibility, experimentation, and change. The ability to live with noise, to expect it, to incorporate it, is the key to survival. Daily life illustrates this balance. People plan their futures, but they also know that chance events will alter those plans. A storm may cancel a journey, an economic shift may change opportunities, an illness may disrupt routines. These events are not predictable in detail, but probability helps humans prepare. Insurance, medicine, and policy are all ways of managing noise at the level of society. At the personal level, uncertainty gives life its texture. Without unpredictability, there would be no surprise, no suspense, no joy in discovery. A world without noise would be a world without possibility. Science has taught humanity to see noise not as disorder, but as part of the deeper order of reality. Probability and uncertainty are woven into the universe, from atoms to galaxies. To resist this truth is to cling to an illusion of control. To embrace it is to recognize that uncertainty is the condition of complexity, the foundation of creativity, and the source of resilience. Living with uncertainty is not resignation. It is participation in a world that is dynamic, open, and alive with possibility. To see uncertainty not as an obstacle but as a foundation requires a shift in perspective as profound as any scientific revolution. For centuries, human beings sought absolute certainty, hoping that deeper knowledge would strip away every layer of unpredictability. Yet the closer science looked at the universe, the more it found randomness at the root. Atoms do not move in perfectly predictable paths. Particles do not reveal definite properties until measured, and even the structure of galaxies owes its existence to fluctuations magnified from the quantum vacuum. Certainty, once imagined as the bedrock of reality, is now understood as an emergent quality built upon layers of noise. This realization does not make the universe meaningless. On the contrary, it reveals that meaning is created in the balance between order and randomness. The laws of physics are not rigid scripts, but frameworks of probability. They set the stage upon which fluctuations play, shaping outcomes without dictating them in detail. In this interplay lies the richness of reality, Without randomness, the cosmos would be frozen in inevitability. Without order, it would dissolve into chaos. Life, thought, and discovery exist only because the universe is noisy. Science itself has grown stronger by embracing this truth. Instead of demanding perfect prediction, it accepts uncertainty and works with it. Experiments report margins of error, probabilities of success, and confidence intervals. These are not signs of weakness, but of honesty, reflections of a universe that cannot be compressed into absolutes. The power of science lies in its ability to make reliable predictions even when certainty is impossible, to find order within randomness, and to turn noise into knowledge. For individuals, the lesson is both humbling and liberating. No one can know the future with certainty. Chance events will always shape the course of life. But within this uncertainty lies freedom, creativity, and resilience. The unpredictability that prevents total control also ensures that new possibilities are always open. Just as galaxies emerged from quantum fluctuations, so too can new ideas, new choices, and new paths emerge from the noise of daily life. As this journey draws to a close, the image of reality that emerges is not one of silence and precision, but of motion and possibility. The universe is alive with fluctuations, restless at every scale. From the flicker of virtual particles in a vacuum to the vast filaments of galaxies, stretching across billions of light years, noise is the condition of existence. To live with fundamental uncertainty is not to live without meaning. It is to recognize that meaning arises because the universe is not fixed, because it allows for novelty, growth, and change. Quantum noise is not an imperfection in the design of reality. It is the design, it is the hum of creation, the whisper that becomes galaxies, the flicker that becomes thought, the variability that becomes life. To embrace it is to see the universe as it is, not a flawless machine, but a dynamic process, not a closed script, but an open story. And it is within that story, written in uncertainty, that humanity finds its place.